When you look around the digital world, websites, apps, all that stuff, so much of what you're seeing isn't just a static picture. It's actually code, dynamic, scalable, editable code. We're talking vector graphics, things like SVGs. And the power there, representing designs as code that's independent of resolution, instead of just fixed pixels. It's pretty incredible. But here's where it gets really interesting. Taking something visual that isn't code, like a photo maybe, or a quick sketch, or even just text describing a design, and turning that into this precise editable code. That's a tough challenge. It's sometimes called inverse rendering code generation. Now, vision language models, VLMs, they seem almost perfect for this, right? They bridge images, text, and code. So they can sort of frame this task as generating a program, a sequence of code to draw something. But here's the catch, and this is really the core problem we're going to dig into today. Even the smartest VLMs right now often create SVGs that aren't quite right, or they're just super inefficient. And the basic reason is kind of surprising. During their training, they don't actually look at what their code produces. They never see the rendered image. They learn the SVG syntax, the rules, but they don't get feedback on whether the drawing itself looks good.
Yeah, that's spot on. That lack of visual feedback, it's a huge blind spot in the learning process, and it leads to real problems. The model might hallucinate shapes that weren't there originally, or maybe get stuck repeating bits of code over and over, or just struggles to generalize what it learned to new inputs that are even slightly different. They get good at writing the code, the sequence, but they don't really connect it to the visual result. And you can't easily just borrow standard techniques from other graphics areas, like differentiable rendering. Those usually work by adjusting continuous values, like the position or size of a shape. But VLMs generate code one discrete token at a time. It's a different kind of process.
Okay. So it's like they're learning to write the instructions for building something, but they never actually check if the final product looks like the blueprint. They're drawing blindfolded during practice, essentially.
That's a good way to put it.
Okay, so this brings us to the source material for today's deep dive. It's a paper introducing a method called RLRF. That stands for Reinforcement Learning from Rendering Feedback. The name kind of gives away, right? The whole idea is to finally give these code-generating models a way to see the results of their work and actually learn from that visual output. So our mission today is to unpack this RLRF approach. We'll look at how it works, the clever ways they use this rendering feedback as a reward signal in reinforcement learning, and really see how much it improves the AI's ability to generate vector graphics that are accurate, efficient, and, just look good, whether from images or text. Consider this your shortcut to getting up to speed on a really cutting-edge technique that merges AI learning with visual design. So, thinking about that potential, again, generating designs as code, SVGs specifically. The benefits are huge, right? Small files, easy editing, scales perfectly. It really is like giving AI a programmable design tool. And like we said, VLMs are already being used for this, framing it as code generation. They've shown some promise, capturing the big picture and even some details, because they work across vision, language, and code.
Right. But that critical limitation, the drawing blind part you mentioned, that's the sticking point with standard methods. Their training is mostly driven by comparing the generated code sequence to a target code sequence, like predicting the next word or token in the sequence. So they learn the grammar, they learn about circle and polygon primitives and how to structure the SVG file. But there's no direct learning signal connected to the visual outcome of running that code. And in practice, that means you get errors, misaligned shapes, things that just look off compared to the input. Plus, a really big one is code inefficiency. You'd think these learning methods would be smarter than old school image tracing, right? Those tracing methods can spit out SVGs with tens of thousands of tokens, just massive files. But standard VLM training doesn't automatically push the model to be concise. It might generate really verbose code if that happens to match the training data structure. And the technical reason this is tricky is that generating code token by token, it's just not differentiable when you factor in the rendering step. You can render the final SVG, sure, but you can't easily calculate how a tiny pixel error in that rendered image should change the specific token choices the model made way back at the beginning. Things like differentiable renderers like diffVG, they exist, but they work differently. They optimize continuous parameters, not discrete code tokens.
Okay, so standard training is like learning grammar by just reading books, but never actually speaking and getting corrected on whether people understand you. That really clarifies the gap. So RLRF, it's about building that bridge, letting the model run its code, see the output, and learn from that.
Exactly. That's the core idea of RLRF. They bake that rendering step right into a reinforcement learning loop. Even though you can't do standard backpropagation through rendering discrete tokens, you can render the output and then use that rendered image to calculate a reward signal. How good was this attempt? So here's roughly how it works, step by step. You give the model an input, an image to vectorize, or maybe a text prompt. The VLM then generates not just one SVG, but a bunch of possibilities. Think of them as different attempts or rollouts. Each one of those generated SVG code snippets is then rendered into an actual pixel image using a standard render, like actually drawn out. Then comes the feedback. These rendered images are compared back to the original input, the source image, or the text prompt. Based on how well they match, a numerical reward score is calculated for each attempt. This reward basically tells the model this attempt was good or this one was not so good. Finally, reinforcement learning, they use an algorithm called GRPO in the paper, uses these reward signals to update the VLM. It learns to adjust its strategy, making it more likely to generate SVGs that result in high reward rendered images next time. But it's not just pure RL from scratch. They found a two-stage approach works best. Stage 1 is critical, supervised fine-tuning, or SVG-SFT. This is more traditional training. They fine-tune the VLM on lots of pairs of images and existing good quality SVGs, usually human-created ones. This first stage teaches the model the basic language of SVG, the syntax, the structure. It gives it what they call SVG fluency. And the ablation studies they did just showed this is absolutely essential. You can't just jump into RL without this foundation. The model doesn't know enough to even start generating plausible SVGs.
Oh, okay. So SFT builds the foundation, teaches it the vocabulary and grammar.
Exactly. And then stage 2 is RLRF. That's where the refinement happens. You take that fluent SFT model, and now you apply the reinforcement learning loop with the rendering feedback. The main goal here is to maximize that rendering reward, making the outputs look better. They also use some tricks like KL regularization to make sure the model doesn't stray too far from what it learned during SFT, keeping the learning stable, though they mention in ablations they could even remove that sometimes.
Got it. So SST is like the textbook learning. RLRF is like the practical application with real-world feedback. You learn the rules and you practice and get critiqued on the outcome. Makes perfect sense. Now, you mentioned calculating that reward. How do you actually tell the AI if an SVG is good? It feels like it's got to be more than just like pixel-perfect matching.
You've absolutely hit on a key point there. A truly good SVG needs to be visually accurate, yes, but it also needs to capture the right meaning, the semantics, and the code itself should be efficient, not bloated. So they designed this really clever composite reward function. It combines signals from multiple different ways of evaluating the output. Okay, first, there's image reconstruction. This is the direct comparison. How close are the pixels in the rendered image to the pixels in the input image? They use standard things like L2 distance, but they normalize it carefully. And critically, they also use an L2 canny variant.
Canny. Like the edge detector.
Exactly. They run the canny edge detector on both the rendered image and the input image and then compare the edge maps. This gives the model specific feedback on how well it's aligning the structures and sharp edges, not just flat color areas. It's feedback on the drawing's structure.
Smart. Okay, what else?
Second component, semantic similarity. Does the rendered image mean the same thing or have the same high-level feel? For comparing rendered images back to input images, the image-to-SVG task, they use models like DreamSim. DreamSim is designed to measure perceptual similarity in a way that's closer to how humans judge if two images look alike, beyond just pixels.
Right, more about the content and style.
Yeah, and for comparing rendered images to text prompts, the text-to-SVG task, things like CLIP, which usually work well for text-image comparison, apparently struggled with the abstract style of SVGs. So they did something interesting. They used another VLM as a judge. They basically asked a separate vision language model, how well does this rendered SVG image match this text description? And used its judgment as a reward signal.
Huh, using an AI to judge another AI's output. Okay, what's the third part?
Third is code efficiency. Like we talked about, you don't want massive, messy SVG code if a simpler version works just as well. So they include a penalty based on the length of the generated SVG code measured in tokens. It particularly penalizes code that gets excessively long compared to some reference length, maybe the ground truth if available, or just generally encourages brevity. It helps avoid those huge, unwieldy files.
Okay, so you've got pixel accuracy, especially on edges, semantic meaning match, and code compactness.
Exactly. And the final reward signal that the reinforcement learning uses is a weighted sum of all these parts. They experimented and found, unsurprisingly, that combining all these signals worked much better than relying on just one. Using only pixel matching might miss the semantics. Using only semantics might lead to inaccurate shapes. And without the length penalty, you get bloated code. This composite approach pushes the model towards generating SVGs that are accurate, meaningful, and practical. Oh, and for the actual rendering part, turning the SVG code into pixels for comparison, they used a standard library called SVG.
Right, okay, so it's not just one score, it's this blend. Does it look right pixel-wise? Does it feel right semantically? And is the underlying code any good? That composite reward sounds like the secret sauce for getting genuinely useful SVGs. All right, this is the exciting part. We've got this two-stage training, this smart composite reward, this rendering feedback loop. Did it actually work? When they put RLRF to the test, what did the results look like? Well, looking at their image-to-SVG results, especially in the tables they provided, yeah, it seems to make a pretty big difference. They compared models fine-tuned with RLRF against the same models trained only with the initial supervised step, SVG-SFT, and also against other existing VLMs, both open and closed source, and even those traditional image processing vectorization methods. The RLRF refined models consistently came out on top across a bunch of different metrics. Things measuring pixel differences like MSE, structural similarity like SNVM, even perceptual similarity metrics like DINO and LPIPS. You see error rates dropping significantly. And importantly, the code efficiency score shot way up, especially for some of the models they tested. The generated SVGs got much more compact. And it's really interesting when you compare RLRF to those older image processing methods like tracing algorithms. Those tracers might sometimes get the absolute lowest pixel error on very simple icon-like images because they're just meticulously tracing every edge. But the code they produce is often enormous, like ridiculously huge. They mentioned one method producing code nearly 100,000 tokens shorter with RLRF. So the tracers generate these massive unstructured files that are hard to edit or use. RLR finds a much better balance, high visual quality, and much more reasonable, structured code.
Absolutely. And beyond just doing well on the specific kind of data it was trained heavily on, the generalization results were quite striking. They tested the RLRF models on data sets of SVGs they had not seen during the main training phases, things like SVG emojis, fonts, icons. And even on these out-of-distribution data sets, the models improved with RLRF compared to their SFT-only versions. That really suggests the rendering feedback isn't just teaching the model to memorize or overfit to the training examples. It seems to be teaching a more general understanding of how SVG code translates into visual structure, which it can then apply to new styles and shapes.
That's a strong sign. It's learning something fundamental.
Definitely. And they also showed promising results for text-to-SVG. Using that VLM as a judge-reward strategy during RLRF, they could take models, even text-only models that hadn't seen SVGs during supervised training, and get them to generate SVGs that aligned well with text prompts. These RLRF trained models apparently did better at capturing details and spatial layouts described in text compared to some much larger general-purpose models that sometimes struggle with generating structured graphics from text alone. They use specific metrics and that VLM judge to quantify this.
Wow, so it even helps bridge the gap from pure text to structured visual code. That generalization piece feels really significant. It's not just about making better SVGs from images, it's learning a deeper connection between code and visuals. So let's dig a bit into the mechanics. What do their experiments reveal about why RLRF works so well? What are the key ingredients or design choices needed to make this learning process effective?
Yeah, the ablation studies they included shed light on several important factors. One clear finding was the importance of exploration during the reinforcement learning phase. Basically, letting the model generate more diverse attempts, more rollouts per input, and using a slightly higher randomness or temperature when sampling the code tokens consistently led to better final performance.
So trying more things, even slightly weird things, helps it learn faster.
Essentially, yes. More variety in the attempts gives the reward function more information to distinguish good strategies from bad ones. It helps the model explore the possibility space more effectively. Another crucial point, which we touched on earlier, was the absolute necessity of that initial SFT stage. They explicitly tried running RLRF directly on models that were just instruction-tuned without the SVG-SFT pre-training. And it basically failed. The models just didn't have the basic SVG proficiency, as they put it, to generate anything meaningful for the rendering feedback to even work on. So SFT builds the essential foundation, and RLRF then sharpens those skills using the visual feedback. You need both.
Can't skip the fundamentals. Makes sense.
And the third big one was the value of the composite reward. They showed results comparing training with the full composite reward versus using only parts of it, like only pixel matching or only semantic similarity or only the length penalty. The combination consistently outperformed any single component. Using just one type of reward could lead the model to plateau early or ignore other critical aspects, like maybe getting the semantics right but the shapes wrong, or vice versa. The blend is key.
Right, you need to push it in all the right directions simultaneously.
Precisely. And they also mentioned some practical techniques used during training to keep things stable. Like early on, models might generate extremely long looping sequences, so they used a dynamic schedule for the maximum allowed sequence length to prevent that.
Mhm.
And during inference, when actually generating an SVG, they often used a best-of-n approach. Generate, say, 16 different SVG candidates, evaluate them with the reward model, and pick the best one.
So it's a combination of a solid foundation, broad exploration, intelligent, multifaceted feedback, and some practical training tricks. Now, research is never perfectly smooth sailing. What kinds of challenges or maybe unexpected problems did they encounter when developing or training RLRF? Any weird behaviors?
Oh yeah, there were definitely hurdles. A classic one in RL is reward hacking. The model finds a clever loophole to get a high reward score without actually doing what you intended. They mentioned a couple of examples. One was the small view box hack. The model learned that if it defined a tiny coordinate system, the view box, in the SVG, the rendered image would be physically very small. And sometimes, depending on how the image comparison metrics were normalized, this tiny image could get artificially high similarity scores.
Ah, sneaky. How did they fix that?
They enforced a fixed rendering resolution based on the input image size, regardless of the SVG's internal view box. So the model couldn't cheat by making the output tiny. Another one was the SVG length collapse. That penalty for making the code too long. If weighted too heavily, the model would just give up and generate super short, completely useless SVG code to minimize the penalty.
So it overcorrected.
Exactly. They had to carefully tune the weighting of that length reward component in the composite signal to discourage excessive length without causing it to just collapse entirely. And for text-to-SVG, they found models trying to cheat the text-image similarity score by literally just writing the input prompt text directly into the SVG using the text element.
Well, that's clever in a way,
Yeah,
but not the point.
right. So they had to specifically strip out any text elements before calculating the image-based similarity rewards and rely more heavily on that VLM as a judge, which could better assess the visual representation of the prompt. Beyond reward hacking, they also noted that on extremely complex input images, the models can still sometimes struggle. They might get stuck in repetitive loops, diverge, or just fail to capture all the intricate details accurately. This suggests that maybe the training data needs even more diversity and complexity to handle those really tough cases.
A long tail of complexity is always a challenge.
For sure. And finally, there's an efficiency consideration. The GRPO training process itself, because it involves generating and rendering potentially many rollouts for every single training input. It can be bottlenecked by that generation and rendering time. This can lead to the GPU sitting idle, waiting for those steps to complete, making the overall training potentially slower than methods based purely on token prediction.
Right, the feedback loop adds computational overhead. Those reward hacking examples are fascinating, though. Classic AI finding the path of least resistance to the reward number, even if it breaks the spirit of the task. You really have to anticipate those exploits.
Okay, let's zoom out a bit. We focused on SVGs. But this core idea, generate code, render the output, get feedback, learn, feels like it could apply much more broadly, couldn't it? What are the bigger picture implications here?
Absolutely. I think that's one of the most exciting aspects of this work. The RLRF framework itself isn't really SVG specific. The fundamental principle is using reinforcement learning, where the reward comes from evaluating the output of generated code, especially when that output is visual or has some complex structure. You could potentially apply this to so many other areas. Think about generating code for web pages, HTML, CSS, maybe even JavaScript. You could render the web page, evaluate its appearance or functionality, and use that as feedback.
Like, does the layout look right? Do the buttons work? Exactly. Or generating latex or TIC-C code for scientific figures. Render the figure. Check if it matches the data or description, or maybe even code for 3D models. Render the 3D model. Compare it to a target shape or description. CAD modeling instructions. Instructions for robotic assembly. Basically, any task where an AI generates structured code or instructions that result in a perceptible, evaluatable outcome could potentially benefit from this kind of feedback loop. This paper offers a sort of general blueprint for improving AI systems that synthesize structured, code-driven outputs, particularly visual ones.
And that really does feel like a significant shift, doesn't it? It moves AI beyond just being a pattern matcher on code sequences towards systems that have some understanding, even if indirect, of the consequences of the code they generate in the visual or physical world. It feels like a step towards AI being more of a collaborator in creative and technical work, not just a code parrot.
I think that's a great way to frame it. It's about grounding the code generation in the reality of its outcome.
Okay, let's wrap this up and bring it back for you, our listener. We've gone pretty deep today. We started with that key challenge, AI generating visual code, like SVGs, often without any feedback on whether the final picture actually looks right, drawing blindfolded. Then we explored RLRF reinforcement learning, or rendering feedback, this really neat solution that gives the AI eyes, in a sense. We saw how it works. Generate code drafts, render them into images, evaluate those images using a smart multi-part reward signal, checking pixels, meaning, and code efficiency, and then use that feedback to train the AI generator to do better next time. And the key takeaway here is pretty powerful. By letting these models see the results of their code, even indirectly through this reward mechanism, we can significantly boost the quality, the efficiency, and even the ability of AI to generalize when it's generating visual code. This isn't just some small technical adjustment. It feels like a fundamental step towards AI systems that don't just manipulate symbols, but actually connect those symbols to the visual reality they represent, moving from code generation towards potentially visual creation.
And maybe leave you with this thought. Think about all the ways we use computers to create things where structured code underlies a visual or complex output. Web design, data visualization, engineering diagrams, maybe even things like music notation or architectural plans. If AI can get better at these tasks by learning directly from the outcome of its generated code through these kinds of rendering-aware feedback loops, where else could this unlock new creative and technical possibilities we haven't even thought of yet?
That's a great place to leave it. Thank you for joining us for this deep dive into RLRF and this fascinating idea of AI learning to see the results of its own code. Definitely something to reflect on how giving AI eyes could change the future of digital creation.